Hello everybody, welcome back. This video is the second in a series I'm doing on the control systems and running gear on my 6-wheel Rover. If you haven't seen the first video where I talked about the construction of the chassis and most of the running gear, I'll put a link to that video in the description below, or if I can figure it out, I may put it somewhere here on the screen. I don't know. We'll see what happens with that. But in either case, I'll put it in the description below. And so now I want to get into the GPS and the compass. So anyway, we'll start piecing this thing back together. Before I get too far into it though, I want to take a little trip back in the past and just show you a little piece of history I have here. This is the Honeywell HMR 3000 fluid stabilized magnetic compass module. This is the compass that was in the DARPA Grand Challenge vehicle I started building around 2001. It was mounted on that car, and I think I got a picture I may be able to put up too, where I can point out where it was on the vehicle. And what I wanted to show you first is just the physical size of this thing. And basically what it has in it is a series of magnetometers, essentially just coils of wire that can sense the Earth's magnetic fields, and essentially just, you know, having a coil of wire in each of the 3 axes of rotation, it can orient itself relative to Earth's magnetic field and works just like the compass you might use when you're hiking or something, except only this one has a serial input port here. This particular module was not cheap. It cost several $100s, and it was the best I could find that I could afford back in the time. This was intended to be used on boats and planes and things like that, and to be connected into their navigation systems. I integrated it into the microcontrollers that were controlling my vehicle. But I want to show you the tilt compensation on this, because the thing with these magnetometers is they can sense the Earth's magnetic field, but they're assuming that those lines of magnetic flux in the atmosphere are running more or less parallel overhead to where you are. So the thing is, if you take this unit and you tilt it in relation to those lines, it confuses the magnetometers so they get the wrong reading. So you have to have some way of sensing if the unit's tilting in one direction or another, and then working out the math in order to compensate for that. And what's interesting about this unit is this is the board out of that unit. This is the tilt sensor that gives it that input, and it's such an amazing little device because it's actually called a electrolytic fluid tilt sensor, and all it is 4 metal rods set at right angles to each other, and kind of like a cross pattern, inside of a chamber, and there's just an electrolyte fluid in there. And so you can imagine electrolyte, you know, is somewhat conductive, and so when you have these 4 rods in there with the fluid, you can read the resistance relative between those 4 rods, and if you were to then tilt that chamber, you would be exposing the rods on this side to more fluid than the rods over here, and your microcontroller can compare those differences in resistance and give you a pretty good resolution of the tilt in that axis. And so this would be a 2-axis tilt compensation, and this sensor allows it to do that. And then the other electronics on this board, you would have your magnetometers, and then this board has its own microcontroller that again crunches those numbers and combines basically the readings of the tilt sensor and the magnetometers to give you a fairly decent direction indication, regardless of whether or not this thing is tilted along any particular axis. And I think it's good up to plus minus 60 degrees on that tilt. So it's a very neat and featured packed, you know, little unit. But what I wanted to stress is just the size of it, you know, and kind of as ingenious of a solution as this is on this tilt sensor, it seems kind of archaic by today's standards, because we all have these in our phones now, and that little sensor right there, this entire unit, is probably now equal to something that's about the size of your little fingernail, or maybe even smaller. So to me, that's just incredible how things have changed. And for as much as that unit cost me back in the early 2000s, and as hard as it was for me to find something like that I even had access to that I could use, to give you a comparison, this is the compass that I'm using on this latest Rover, and it too is a tilt compensated magnetic compass. It also has magnetometers and a tilt sensor and a microcontroller to do all the math for me, and it's all packaged on something about the size of a quarter there, an American quarter. So I just thought that was pretty interesting. And this is the same unit that is actually mounted on the vehicle. So we'll go over how everything's mounted on the vehicle now real quick here. I'll start with this antenna mast, or this compass mast, just to get it out of the way. So as you might have seen me mention in previous videos, the compass for this car is mounted on a steerable mast. In other words, it's connected down here at the bottom through this linkage to the steering linkage, so that the compass mimics the direction of the steered axle. And what that does for me is it eliminates overhead on my Arduino. It doesn't have to work out the difference between that. If you think about when you're driving a wheeled vehicle, the vehicle is not necessarily following the direction of the chassis itself. It's following the direction of wherever the wheels are pointed. So when you're going into a turn, the wheel's going to point toward the direction they're going first. And that's the direction I want my compass to read. I want to know that when I issue a steering command, that the compass is pointing to where I steered, and that when it gets there, I can stop steering. Now, even though the car may still be, like in this situation, if my wheels are pointing 30 degrees to the left there, the car's still pointing straight ahead. As long as the wheels are going 30 degrees to the left, the car is eventually going to get there. It's just going to trail behind wherever the front wheels are steering. If I had the compass mounted rigidly to the chassis, then the front wheels would steer 30 degrees to the left, and the car would continue turning that way until it got there. But by that time, the car would be steered way, it would oversteer basically, and it would have to compensate and find its way back. Having the compass steer with the wheels keeps it from oversteering. The minute the wheels are going the direction they're supposed to go, the microcontroller knows to stop issuing a steering command and start counter steering and straighten the wheels out. That could all be modeled, in software, if you didn't want to go to the hassle of having to make a mechanical connection to the steering on your compass. But the truth is, this works really well. There's no latency. Again, it takes more overhead off of your microcontroller. You don't have to worry about it doing that extra little bit of math there. And I had no reason not to do this, because using this type of magnetometer-based compass, for me, it's always worked out better to have the thing mounted up on a mast away from the rest of the vehicle anyway, because you have what's called hard iron offsets. Any ferrous metals that are around these magnetometers have to be compensated for. You have to calibrate the unit and calibrate those hard iron fields away from your magnetometers so that they give an accurate reading regardless of your orientation. They will influence that. Also, anything with a magnet in it will greatly influence what this is doing. So even though this vehicle is mostly made out of aluminum and plastic, there's some pretty powerful magnets in the drive motor. So it behooves me to put this compass as far from the drive motor as I can, and that's why I mounted it on this mast. It just so happened that the bottom of the mast ended up being in close proximity to the steering linkage anyway, so it was not a big deal to mount this to the steering, and it just happens to work really well for me that way. So the only other few things I have still on this panel here, I wanted to show here on the other side. This is the steering servo mixer cable I was telling you about. The wiring to the steering is a little complicated because I do have 4 servos controlling the 4 steered wheels at each corner. And this is the mixer that basically connects to the front pair of servos and then to the rear pair of servos, and I'm able to tune the relative signal between front and rear so that I can coordinate the steering between the front and rear, and it works out pretty well that way. And then the only other thing I have in here is this is a Pololu serial servo controller right down in here, and these are really handy because they serve the same function in that they reduce the overhead on your main microcontroller. So I only want my Arduino, the part that's navigating the vehicle, I just want it concentrating on the navigation. I don't want it to have to be continually feeding servo positions, service routines, and that type of thing. That can get kind of finicky if you're running interrupt routines on your microcontroller or anything that's timing sensitive, and at the same time you're feeding positions to several servos. It can be problematic. These are a great solution to that kind of problem. You just, you can actually configure these. You can plug these in through a USB port and plug them into your laptop, and you can actually configure a lot of parameters on them, such as a single pulse control. You can just have it periodically just send a position signal and then forget about it. It's like set and forget, and it'll go that position, stay there until it gets the next position. Or you can say you want it to be continually updated. You can have it home back to a certain position if it doesn't receive a valid signal within a given time. That's great for doing like kill switches and safeties and like a dead man switch type situation. There's lots of different ways you can configure these themselves, and that puts a lot of smarts in a package that's completely separate from your main microcontroller. And for the price, they're just really handy to use. I use them a lot in a lot of my different projects, just because they're so simple to use and so versatile in the different ways you can configure them. It opens up a lot of avenues for that. So that's basically what's on this board that goes on top of the chassis. And next we'll show the next thing in the bottom of that board is the Arduino board that I'm using. This comes from Sparkfun. It looks very similar to the form factor you might have seen for a lot of Arduinos. This is called a RedBoard Turbo. They have a RedBoard. This is a RedBoard Turbo because it has the SAMD21 chip in it, which gives you a lot of really interesting functionality. The main benefit that I've found with these is that they have several additional programmable communication ports that you can use. You can set up several of these different pins on their own bank of communication ports to give you the opportunity to have like multiple I2C connections, multiple SPI serial connections, UARTs, whatever you need. It gives you a lot of options to do that. So I like to use it for my robots because I can't always just daisy chain I2C connections together. A lot of things I use, like the serial servo controller, it uses a serial connection. So it's good to have all those options, and that's why I'm using this board. You might see a couple extra components on here. This is just a level shifter because this is a 3-volt board. So the ins and outs are 3 volt on this. So this is a level shifter because the serial servo controller is expecting to see 5 volts. So it's doing that. And then this is a voltage regulator, just a large, I think it's a 3-watt voltage regulator for supplying all the other electronics, because I hooked it up here just because it's a convenient place to plug other things into. I kind of reconfigured some of the headers on here so I could use them as a kind of a voltage source for other things, but that's all that's going on with this board. And then plugged on top of the microcontroller board there is this, is like a shield, that's what they call them. The shield plugs on top of the other board right there. All the headers are designed to line up. They just sandwich on top of each other. They make all kinds of different sensors and displays and things you can hook up like that. Well, this just happens to be it was a GPS logger shield. It has you can see a little GPS chip here on it and a little SD card slot there. And it was intended to be something you could put in a machine and just log your GPS route if you wanted, and then be able to retrieve it and read it back and do what you want with it. I'm just using it for the SD card reader. I actually disabled the GPS. This is not the GPS I'm using on the card. I'm just using this as my SD card reader. This is the This is the card that actually holds the route file that I follow. So whenever I want to program a new route, you know, I have predetermined paths along the farm I want to take. You know, they generally just follow the different roads. And I'll pop this out and go in on my laptop. And I have different ways of determining what the GPS coordinates are I want to follow. I can walk them out and directly read them out on the ground. I've actually found that I can go on Google Earth and do a pretty good job of pulling coordinates off of Google Earth and building maps. And then it's just the route file is just a list, just a numbered list of latitude and longitude coordinates. There's a few other fields in there. The way that I configure the files, and again, these are things you can write in whatever format you want, but mine are comma delimited latitude and longitude, and then there's a few other fields at the end that use one of them if I want to command a particular speed limit, and there's another field that I use to tell the rover the width of the path if I think it needs to have extra wiggle room or whatever to drive. But I really, for this one, all I'm using is the latitude and longitude. But it's all, the format I use is directly from the format we were using for the DARPA Grand Challenge. That's when I first started writing these GPS route files to test my larger vehicle. And I've just never deviated from that format because I've become so familiar with using it. But it's pretty straightforward. So that's all that's going on this board. This is basically just the thing that reads the route file. And then we already went over the compass. I guess the last thing is the GPS. So this is the u-blox C94-M8P GPS RTK board. And this actually, I bought this as a kit. It came with two of these boards, two GPS antennas, and two of these radio antennas. And the way the kit is intended to be used is that you are to configure one of these boards as a base station and then the other one for your rover. They're identical boards, so you have to, you get to designate which one you want to be your rover and which one you want to be your base. I actually took a Sharpie and put a little R on this one so I won't get them confused. But essentially you buy the kit, and it comes with all the cabling and basically everything you need to get started. You plug this into your laptop and open up there. You know, u-blox has a really extensive development suite, and you go in there and there is probably 1,000 different parameters in this GPS that you can configure, but there are very specific ones that you want to configure to enable the RTCM messages, the correction signals that you're getting from your base station. You want to enable this to receive those. You want to set the rate that they're received at, and you also can set the rate that you get your GPS updates. You can configure what satellite constellations you're watching. There are so many parameters, it's mind-boggling. But when you're working with a microcontroller, especially something like a little Arduino, what's important to know when you're configuring these is that pipeline that's going to your Arduino, you don't want to jam it full of too much information. I mean, you can, it's really easy to. So part of the secret is learning to only extract the information that's essential to the mission. And I'm probably going to do separate videos on that specific thing. And actually, I think I'll put a link below to a guy that I saw on YouTube who actually introduced me to this system. And he does a really good job of laying out in detail how you configure all that. So I'll put a link to that down below in the description as well. And if you want to follow up on that, because my goal is for people to be able to get the information they need to at least start down the path of configuring their own navigation algorithms and stuff without having to plug into somebody else's Orange Cube or ArduPilot, or those are all great plug and play solutions. And I realize they have their own challenges with how you have to configure them and everything. But I want people to have a better appreciation for what's going on under the hood. The math and the geometry and the trigonometry and the number crunching and all the little problems you have to solve in order to get this relatively simple function to happen reliably. And it's just something I enjoyed doing years ago when I started with the DARPA program. And back then we didn't have those off-the-shelf solutions. Everybody was creating their own code and having to think through all these problems. And it's wonderful that that is so accessible to people now. But I still want people to have an understanding of what's actually happening in that code, because it has its applications in lots of other places than just navigating vehicles around. And again, that's something that I will probably share in future videos, is some of the other applications that I'm putting GPS to work doing here on the farm. A lot of the things we do on the farm are very position critical. They can be very time critical. And it so happens that GPS is a great resource for position and time references. So the more familiarity you have with that type of thing, if you're the type of person that's inclined to building any kind of equipment or instrumentation that needs that type of reference, it's beneficial to know the ins and outs of working with these raw GPS strings. It's not all that difficult. It could be as difficult as you want it to be, but it's the nuts and bolts are pretty straightforward. So we'll cover more of that later, but for now I think that'll be it. I think my next video I'm going to go over reassembling all this back onto the vehicle, and maybe we'll shoot a little more vehicle video of it running around. So I appreciate your sitting with me through all this. And I thank you for tuning in, and I'll see you on the next one. Bye-bye.